multiplied by my characteristic length that I calculated last week, divided by my conductivity of the metal that's given in the problem. My Biot number for this case is going to be 0.002 435 second minus 1. This value is lower than 0.1, therefore I can apply lumped capacitance. To apply the lumped capacity analysis, I need to find my constant B. The V stands for volume. We know that the relationship between area and volume in this case is my characteristic length, so this equation is going to be reduced to my heat transfer coefficient divided by density, specific heat, characteristic length. Therefore, my B constant is going to be 30 watts per meter squared divided by 2,800, that's the density given in the problem, multiplied by 800 joules per kilogram Kelvin, that's my specific heat, multiplied by my characteristic length. So my constant B is going to be, I'm really sorry, I made a mistake here. I copied the value from the wrong place. My Biot number is 0.0008333. Okay, I'm really sorry about that. The value I put there was this one, 0.00245 second minus 1. Just a small mistake here. Having the value for B, I can finally apply my equation for the lump capacitance. That tells that my temperature of the surface at a certain time minus my temperature of the air divided by my temperature of the surface at the beginning of my process minus temperature of the air is equal to E minus BT, the power of minus BT. We know everything. What we want to find is the temperature of the surface after a certain time, our time here being 2 minutes. I want to know my temperature of the surface at 120 seconds. Going to be my temperature of the air plus temperature of the surface at the beginning of the process minus my temperature of the air multiplied by my E in the power of minus BT. My temperature of the surface at 120 seconds is going to be 5 degrees Celsius, that's my temperature of the air, plus my temperature of the surface at the beginning of the process, 300, minus my temperature of the surface, my temperature of the air, sorry. All that multiplied by my E, my exponent, of minus my value of B, 0.002435 second minus 1, multiplied by my time, that's 120 seconds. Seconds cancel seconds minus 1. So my temperature of the surface at 120 seconds is going to be 225.3 degrees Celsius. And I can use this value to find my temperature gradient. Well, we are talking here about my metal plate, and I'm talking about convection as well. Remember that when we are talking about my no-slip condition, I can say that my heat transfer due to convection in the first layer in the plate is the same amount of heat transfer that I have due to the convection up here is the same amount of conduction in this first layer because my first layer has a velocity is equal to 0. So I can say that minus K, temperature gradient, when my y equal to 0, so at the surface is equal H, temperature of the surface at a certain time, minus temperature of the air. What I want to find is my temperature gradient, so it's this term here. So my temperature gradient at this surface is going to be equal to this minus K goes to the other side here, multiplying, or dividing. It's going to be convection coefficient multiplied by my temperature of the surface at a certain time, that's my 120 seconds, minus temperature of the air, all that divided by my K of the metal, conductivity of the metal. I'm talking about the surface of the metal. So my temperature gradient is going to be 13 watts per meter square Kelvin multiplied by 225.3, that's the temperature that we calculated, minus 5, divided by my K of the metal. So my temperature gradient is going to be minus 36.7 kelvins per meter. How my temperature is changing as a function of my distance. Okay. Everything all right with this one? I just wanted to finish this one quickly before we go to the next ones. Any questions on this one before we move on? Okay. We are going to move on to chapter 7 today. Have you studied chapter 7 already? Yes, no? As Anthony covered, external force convection already, chapter 7. Okay, thank you. Thank you, Akam. So he covered, that's great. It's not going to be anything new then. What chapter are you this week? What was the last chapter that Anthony covered with you? Okay. So, a transformer that is 10 centimeters long, they're giving us the size of the transformer. And 6.2 centimeters wide. So here we have our sizes, okay? Is to be cooled by attached fins. Okay. And we're given the dimension of these fins. My fins are 10 centimeters by 6.2 centimeters with a thickness of 2 millimeters. Okay. The emissivity of my heat sink is 0.03. What else we are told? The height of my fins. The height of my fins is 5 millimeters. And I'm told that a fan blows air at 25 degrees Celsius. So I'm given the temperature of air up to chapter 9. Thank you very much, I can. So I'm told that I have air blowing at a temperature of 25 degrees Celsius. The passages between those fins. So I'm blowing air through those empty spaces here to cool down my transformer. This is my transformer. The heat sink is to dissipate 12 watts of heat. So I know my heat rate. I know that I want to dissipate a heat rate of 12 watts. And that the base of the heat sink, so my temperature here, is not to exceed 60 degrees Celsius. My temperature of the surface can't be higher than 60 degrees Celsius. Assuming the fins and the base plate to be nearly isothermal. I'm going to have some assumptions here. Isothermal. If my fins are isothermal, what does it imply? What does it tell me about the efficiency of my fins? Does anyone remember? So if I'm told that my fins are isothermal, I can assume that my fin efficiency is 1. Okay? Just remember that, okay? Every single word in this problem can help us with something. In this case, when they tell us that the base plate and the fins are nearly isothermal, it means that my efficiency is 1. And the radiation heat transfer is to be negligible. So I'm also assuming that my Q of radiation is equal to 0. So negligible radiation. What else I'm assuming here? I'm going to assume as well that I'm operating in steady state. So there is no transients. Determine the minimum free stream velocity of the fan that needs to supply to avoid overheating. Assume the flow is laminar over the entire fin surface of the transformer. I'm told that is laminar. I can verify that after. What else? We're going to assume a pressure to be atmospheric. That allows me to read the data for the air at atmospheric pressure from the tables. Okay, so those are my main assumptions here. The most important one, I would say, is remembering that if your fins and heat are and the plate are isothermal, my efficiency of the fins is equal to 1. Okay. Well, what I want to find in the end, my velocity of the air. For me to find the velocity of the air, I need to find my Reynolds number. For me to find the Reynolds number, I need to find my Nusselt number. For me to find the Nusselt number, I need to find my age of convection, okay? So let's first focusing on finding my convection heat transfer coefficient. I'm going to kind of separate that in steps, okay? So my step 1 is going to be finding my film temperature. Why? Because I need to read my data for the air at the film temperature. My film temperature, temperature of the surface plus temperature of the air divided by 2. I'm told that the air temperature is 25 degrees Celsius, right? And the surface temperature is 60 degrees Celsius. 25 plus 60 divided by 2. So my temperature of the air, of my temperature film is going to be 42.5 degrees Celsius. Okay. Having my film temperature, I can go to my book, table A15, and read my air properties. What properties I'm going to read? I'm going to read the conductivity, I'm not going to do the readings because I believe you know how to do that, okay? 2681, sorry. If you have any questions about how to do any of those things, just let me know. My viscosity, my kinematic viscosity, 1.726 times 10 to the minus 5 square meters per second. I'm going to need that for the Reynolds number. And the product, 0.7248. Okay, my third step is to find my heat transfer surface. Surface area of heat transfer. Okay, I want to know what area is involved in my heat transfer. I'm going to have 2 areas involved. I'm going to have my finned area, my unfinned area, and need to sum them. So my area that has fins, well, I have each fin has 2 sides, okay, front and back. And I have 7 fins, so each fin has 2 sides, and I have 7 fins, all that multiplied by the area of one fin, 0.1 meter by 0.005 meter. That's are the dimensions of my fin. Because they are very thin, I'm not going to consider it the top of the fin as heat transfer area, okay? Not here. So I'm going to consider this area in this side and the area in this other side. So my finned area is going to be 0.007 meters square. Okay. Next area I want to find my area unfinned. My area unfinned is my area of the top. So if I had just the block, I would have a block with the sides of 6.2 by 10 centimeters. All this area minus the area occupied by these fins here. So minus the 7 times this area of the top of the fin. Okay, so I need to reduce this area here, because all I want is this area available here. This area here, in between the fins. Okay, so it's the total area of my transformer minus the area from the top view, let's say. So my area unfinned would be my area of the whole transformer, 0.1 by 0.062 meters, minus the number of fins. So I have 7 fins, and each fin is using a space of 0.002. That's my thickness, 2 centimeters, by 0.1 meter. So my area unfinned is going to be 0.0048 meters square. So my total area of heat transfer is the sum of them. My area finned by plus my area unfinned. 0.007 plus 0.0048. So my total area, 0.0118 meters square. This is my total area of heat transfer. Now I'm going to use this area of heat transfer to find my agent of convection, or my overall heat transfer coefficient. In this case, you're not considering radiation, so that would be my age of convection. So my age is going to be my heat rate, my heat transfer coefficient is equal to my heat rate, multiplied by my efficiency of the fin agent, area of the surface, that's my total area, temperature of the air minus temperature of the surface. Well, that would be age of convection is what I want to find, is equal to rate of heat transfer, efficiency, area of the surface, temperature of the air minus temperature of the surface. My rate of heat transfer is my 12 watts that I want to dissipate. Is how much heat transfer I want to dissipate, how much heat I want to dissipate. My efficiency is 1. My total area of heat transfer is 0.0118 meters square. Temperature of the surface minus temperature of the air minus temperature of the surface minus the air. Sorry, I think I inverted here. Surface minus air in this case. Okay. The only difference if you invert here is that you're going to get a negative number that is expressing that you are losing heat, okay? That's the only difference, this signal. So your age of convection is 29.06 watts per meters square degrees Celsius. Now I can use this age to find my Nusselt number. I know that my Nusselt number is equal age of convection multiplied by my length divided by my conductivity. For the Nusselt number, we use the conductivity of the air, okay, of the fluid. So my Nusselt number is going to be my age of convection, 29.06 watts per meter degrees Celsius, multiplied by 0.1 meters. That's the total length of my plate of my fin, divided by 0.02681 watts per meter degrees Celsius. Okay, watts cancel watts, meters degrees Celsius. So my Nusselt number is going to be 108.4. And now I can use my Nusselt number to find my Reynolds number, okay? How? I'm going to find an adequate relationship between Nusselt number and Reynolds number for the flow that we are talking about. What considerations do we have in this flow? Here we are talking about flow over a flat plate, laminar, and isothermal. If you go to the book, you're going to see that you have the equation 7.21 that fills all those fulfill all those requirements. It's not that straightforward, Alex. Depends on the type of flow. So not always. It is there is a relationship between them, but this relationship is going to depend on the type of flow that you have to get an adequate relationship for each type of flow. In this case, our relationship is Nusselt number is equal to 0.664 multiplied by my Reynolds number for a length. That is because of my plate is a flat plate, so my Reynolds number is a function of a length. In the exponent 0.5, Prandtl number 1/3. So each type of flow may require a different relationship between your Nusselt number and your Reynolds number. Okay, if you go to the summary on the Senja book, you're going to see that on page 453, it has kind of like a summary of some of the relationships. Okay, and endothermal surfaces, flat plate, laminar turbulent. So each one of them is going to have a different relationship. The one I'm using 7.21. No, here, okay. That applies to, it's an average Nusselt number for the entire plate. And this is the relationship applied to the laminar flow. So I want to solve that for my Reynolds number. Because what I want to find here is my Reynolds number. Nusselt squared divided by 0.664 square, Prandtl 2/3. I just manipulated that one to remove the 0.5 from here, okay? It's just maths. 108.4 squared divided by 0.664 square, 0.7248 2/3. So my Reynolds number is going to be 3.302 times 10 in the exponent 4. Now I have a Reynolds number. Now with this Reynolds number, I can find my velocity of the air. So my Reynolds number is a function of a length. So my Reynolds number for a flat plate is equal to my velocity multiplied by my length divided by my kinematic viscosity. This length is the length of the plate. Remember, that's a flat plate we are talking about. So my velocity is equal to my Reynolds number multiplied by my kinematic viscosity divided by my length of the flat plate. So my Reynolds number, sorry, my velocity is going to be 3.302 times 10 to the exponent 4. Kinematic viscosity that we read from the table, 1.726 times 10 to the minus 5 meters squared per second. All that divided by the length of my plate, that is 0.1 meters, that's my 10 centimeters. So my velocity is going to be 5.7 meters per second. Okay. In this case, the only reason it was we could find the relationship between the Reynolds number and the Nusselt number because the problem stated that it was laminar as well, okay? The problem had already told us that we have a laminar flow. I can't remember the Reynolds number in the lab, Alex, because we had very different velocities. We went from 0.5 to 5, 6 meters per second in the forced convection. I'm not sure all of the possibilities were laminar. I can't remember now. Okay, in this case, they were laminar. But in this case, we're talking about flow over a cylinder, not a flat plate. So the relationship is different, okay? This relationship is only for flow over flat plate. The flow over cylinder has a different relationship. No problem. Remember that the Nusselt number relationship depends on the type of flow, depends on the geometry, and depends as well if it's isothermal or not. The Prandtl number came from the table A15. So we read the Prandtl number for the film temperature in the table. From here. Read that from table A15 for the air. This part, Alex? Okay. Any more questions before we move on? We're going to solve another one that involves a flat plate, but this time without fins. Going to be quite similar to this one, so we can fixate the content, try to remember the content. Remember that next week we don't have a live stream of the tutorials. I'm going to leave a recording for a few exercises for 1 hour worth of exercises for next week, okay? We are not going to have a live stream next week. I need to cancel on this online as well. So, consider a hot automotive engine. I'm just going to get a drawing as well for us. My drawings are horrible, so I'd rather just use the book ones. Definitely not good at drawing. I can't draw not as much as a straight line. Consider a hot automotive engine, which can be approximated as a 0.5 high, 0.5 meters wide. So here you don't have the width, but it would be like .5 meters high, 0.4 meters wide, and 0.8 meters long. My dimensions. The bottom surface of the block, this surface here, is at a temperature of 100 degrees Celsius, or 373 Kelvin. And it has an emissivity of 0.95. Remember that in the previous one, they told us that my radiation was negligible. Okay. In this case, they're giving us the emissivity. We might need to use it. The ambient air is at 20 degrees Celsius. And the road surface, I'm going to call that my temperature of the surroundings, my temperature of the surface, is equal to 25 degrees Celsius. Determine the rate of heat transfer from the bottom surface of the engine block by convection and by radiation. It means that I want to find each one of them and then find my total heat transfer by combined convection and radiation. As the car travels at a velocity of 8 kilometers per hour, my velocity of the car is going to equal my velocity of the air, okay? So always when you're talking about the flow around the car, I'm saying that my velocity of the air is the same velocity of the air, okay? First of all, I don't want my velocity in kilometers per hour. I want my velocity in meters per second. So if you multiply by 1,000 divided by 3,600, you're going to get the velocity of 22.22 meters per second. A few assumptions here, okay? And I'm pretty sure Anthony likes to know the assumptions that you're making when solving a problem, okay? So make sure to state your assumption in your exams. I'm assuming here that they're telling me that the flow is turbulent over the entire surface of the block. So I'm assuming, first of all, that I have turbulent flow. I'm also assuming that I have a steady state system. I'm going to assume that it's flow over a flat plate. And when I talk about flow of a flat plate, I'm talking that my critical Reynolds number is equal to 5 times 10 in the 5 for flow over a flat plate. This information is page 113 in case you want to double check. What else could I assume here? I can assume that I have air, and air is an ideal gas with constant properties. Okay. Well, first things first, film temperature.
You are currently the only person in this conference.
I just got a notice here. Is everyone still there? I just got something saying I'm the only person in the conference. I'm going to get, oh, perfect. Thank you. I'm going to find my film temperature between always my surface that's gaining or losing heat, in this case, the engine block, 100 degrees Celsius, and my air, that my temperature of the air is 20. So my film temperature, 60 degrees Celsius. I'm going to then read my air properties at my film temperature in table A15. I'm going to read the same things I read before, my conductivity, viscosity, kinematic viscosity, and the Prandtl number. And the Prandtl number. Let me know if I'm going too fast or if you can't see or understand something, okay? My third step, I'm going to find a Reynolds number. I'm talking here about a flat plate, so in my Reynolds number as a function of a length, okay? That's equation 7.10, page 429. So my Reynolds number as a function of a length is equal to my velocity of the air multiplied by the length divided by my kinematic viscosity. My velocity of the air we already established as 22.2 meters per second multiplied by my length, the length of the block, 0.8 meters. So I'm talking here about my Reynolds number at the end of this 0.8 meters, okay? So I'm calculating my Reynolds number for this exactly length here. That's what it means. Divided by my kinematic viscosity. Okay, so my Reynolds number is going to be 9.376 times 10 in the 5. If my Reynolds critic, my critic Reynolds is 5 times 10 to the 5, I can say that yes, this flow is turbulent. I'm just confirming that it's turbulent, and that's going to help me to choose a relationship for my Nusselt number. So I have turbulent flow over a flat plate. So my Nusselt number, my general relationship for Nusselt number would be AGL divided by K. And the relationship for turbulent flow over a flat plate is 0.037, Reynolds number 0.8, Prandtl 1 divided by 3. Okay. In the book, this one here is equation 7.22. Based on that, I can say that my Nusselt number is equal 0.037 multiplied by my Reynolds number, 9.376 times 10 to the 5, the exponent 0.8, multiplied by my Prandtl number, 0.7202, 1 divided by 3. So my Nusselt number is going to be 1,988. Now I can find this Nusselt number to find my age of convection. My heat transfer coefficient. Nusselt number is equal heat transfer coefficient length divided by my K, the K of the air always. So that if I solve that for my heat transfer coefficient, is going to be conductivity, Nusselt number divided by my length. So my heat transfer coefficient is going to be my conductivity that we read in the table, 0.808 watts per meter degrees Celsius multiplied by 1,988, or that divided by 0.8 meters. My heat transfer coefficient is going to be 69.78 meters square per, watts divided by meters square degrees Celsius. Now we have the heat transfer coefficient. We need to find my area that's subject to heat transfer. Area for my heat transfer. So which area is subject to this airflow? My area of the surface is equal to my, well, is the bottom area, okay? This bottom area has the sides of 0.8 and 0.4 meters. So my area of heat transfer is going to be 0.8 meters multiplied by 0.4 meters. That's 0.32 meters square. Finally, we need to find my Q of convection. applying our Newton law of cooling, Q convection is equal to H area of the surface, temperature of the air minus temperature of the surface. So my convection heat transfer is going to be equal to 69.78 watts per meters squared degrees Celsius multiplied by 0.32 meters square multiplied by 100 minus 20 degrees Celsius. So my convection heat transfer is going to be 1,786 watts. Now, because we have radiation also involved, I need to find my radiation heat transfer, heat rate, sorry, emissivity, area of the surface, Boltzmann constant, temperature of the surface, the exponent 4, minus temperature of the surroundings in the exponent 4. And remember, when I talk about radiation, my temperature must be in Kelvin, okay? There is absolutely no situation where I'm going to feed the temperature here in degrees Celsius. Because of this exponent 4, my temperature must be in Kelvin. My emissivity is 0.95, my area of the surface 0.32. Boltzmann constant 5.67 times 10 to the 8. Temperature of the surface minus temperature of the surroundings. Or in here as well. So my radiation heat transfer, forgot the dot in the top of heat transfer because it's a rate, is equal 198 watts. And finally, my total heat transfer is equal heat transfer due to convection plus my heat transfer due to radiation, because we have here combined the convection and radiation process, where my radiation is much larger than my convection. And here we go. This is our total rate of heat transfer for this situation. Any questions in this one? Would you like me to go back anywhere? Everything all right with this one? We won't be able to finish this one today, but I'm going to start. This is slightly different in terms of the geometry and in terms of the way that our heat transfer is presented to us, okay? A 6 millimeters diameter, so here is my diameter. Transmission line carries an electric current of 50 amperes. We did something similar in the lab as well. And has resistance 0.002 ohm. Although we didn't work with resistance in the labs. Per meter of length. So my resistance is ohm per meter. Determine the surface temperature during a windy day when the temperature of the air is equal to 10 degrees Celsius, and the wind is blowing at 40 kilometers per hour. (283 Kelvin). That, if you convert, it's going to be 11.1 meters per second. I believe you know how to change that, but in case you have any questions, just ask. Well, what I wanted to know here is my surface temperature, okay? To get the surface temperature, I'm going to need my heat transfer coefficient to find my amount of heat transfer as well, my area. Okay, there's quite a few things that are going to need to find that. I'm going to start in a similar way before, but now I don't have my surface temperature, okay? And what's the implication of not having the surface temperature? I can't calculate a film temperature. I can either predict a film temperature using an interactive process, or in this case, I'm going to assume my temperature of the film to be the same temperature of the air, okay? I'm going to assume the film temperature to be 10 degrees Celsius, just to facilitate reading the table, okay? This is one of my assumptions. What else I'm assuming here? That my system is steady, on steady state. Nothing's mentioned about radiation, so I'm going to assume that there is no radiation. I'm assuming here now flow over a cylinder. It's not a flat plate anymore. Now I have a cylinder. And I'm going to assume atmospheric temperature to be able to read the properties for the air. Table A15. I'm going to read the same properties I read before and add the density as well. I'm going to read the density. You don't have to read those properties at the very beginning, okay? You can read them as you go, as you need them. You might not know what you need in the very beginning of your problem. Here, because I already know I'm already reading everything. And the Prandtl number. The very first thing I'm going to do here is find my Reynolds number. Why? Because my Reynolds number is going to tell me if it's laminar or turbulent, and that's going to tell me what relationship I can choose for my Nusselt number. Velocity, diameter divided by viscosity, velocity 11.1 meters per second, diameter 0.006 meters, divided by 1.426 times 10 to the minus 5 meters squared per second. My Reynolds number, 4,675. Well, so for flow across a cylinder, that would be what? Turbulent or laminar? For flow across cylinder in this case, turbulent or laminar? Okay, it's kind of like I just want to show you something. Sorry. In this case, they're not discussing necessarily if it's turbulent or laminar, okay? They're saying that this relationship is for flow over a cylinder and applies for a relationship between for a relationship between Reynolds and Prandtl number higher than 0.2, okay? It's not just related with laminar turbulent in this case, it's related as well to your Reynolds multiplied by your Prandtl number, okay? So in this case, is a very abundant, is a very like comprehensive relationship, okay, that applies for a huge number of Reynolds numbers. But my limitation here is the relationship between Reynolds and Prandtl number, okay? You could verify it by multiply your Reynolds by your Prandtl. That would be 4,675 multiplied by 0.7336, and that would be 3,429, and that this number is higher than 0.2. Therefore, we can use the relationship, equation 7.35. Okay, it's a very comprehensive relationship in this case. I'm just going to write the relationship here, and we're going to finish next week. I think this is one that we used in the lab, Churchill. Five divided by 8. 4 divided by 5. Okay, is this relationship here in the book? This one. Okay, and that's a number for the flow around a cylinder. We have another one for the flow around a sphere here that we are not going to use yet. Copy this equation, or just copy the number of the equation from the book, and you can try to finish that at home, or you can wait for in a few weeks we are going to finish. So we don't have next week. Next week is going to be a recording. I'm not going to finish this one in the recording. I'm going to leave this one to finish here because I want to run through exercise for unit 8 in the recording, okay? That's it. I see you in a few weeks, I think 3-4 weeks, okay? Because then you have the break for Easter. Thank you, everyone. See you. Bye-bye.